Today we're gonna start chapter 2. So last class we just introduced the topic of material science and engineering. But in this class we're gonna start studying, and we said that chapter 1 basically it will not come up in any of the exams or homework, etc. But starting from this chapter, you should expect something. You should expect homework. You should expect something in the quizzes and in the midterm, and so on. Okay. So the title is Atomic Structure and Interatomic Bonding. But before we go into this topic, I just want to give you just an overview of the flow and logic behind the chapters till the midterm, okay? So first of all, we're going to start from a simple single atom. We're going to study a single atom. After that, we're going to study basically the interactions between two atoms, the kind of bonding, the sharing or giving electrons, etc. After that, going from 1 to 2, we're going to study multiple atoms together, how they arrange themselves. After that, we're going to start by asking the question, are all arrangements like this between atoms perfect? The answer is no. So we're going to study these imperfections or defects. So in the first part, we're going to cover it in chapter 2, going from 1 to 2, and going to multiple atoms, we're going to cover it in chapter 3 and 4. And finally, to study these imperfections, we're going to cover it, inshallah ta'ala, in chapter 6. And this is basically till the midterm. After that, I'm going to give you another flow. By the way, if you have any question, you can just raise your hand. I'll be able to see it, inshallah ta'ala. So the objective of this lecture is basically to know the atomic models and basically to understand the electron energy configuration, etc. After that, very important is be able to interpret the interatomic separation diagram and be able to extract some useful information out of it. And finally, to list and note the interatomic bondings exist between materials or between atoms, ions, molecules, etc. So first things first, let's do some revision, I think, from Chemistry 101. So we know the atom has a nucleus. The atom has a nucleus and it has basically electron cloud. And within the nucleus itself, there is a proton and there is a neutron. Regarding the masses, the electron is very small compared to the proton and neutron. It has a mass of 9.11 times 10 to the minus 31 kilogram. The protons and neutrons are heavier, 1.67 to minus 27 kilogram. One clear distinction between elements is the atomic number, or Z. And the atomic number is basically the number of protons in the nucleus of an atom. So for every atom, the number of protons does not change, but the number of neutrons can change, and it will lead to something called isotopes, as we're going to see in a minute. The number of protons in the nucleus is equal to the number of electrons in a neutral atom, okay, in a neutral atom. So in all cases, the atomic number is the same number as the protons, and it is the same number of electrons only in a neutral atom. So this is the first one, the atomic number. The second one is the atomic mass. It's basically the summation between the number of protons and the number of neutrons. And as you can see here, you can see that we put some approximation, which is close approximation, because we did not count the electrons, because the electrons itself is very light, so it will not affect that much the atomic mass. But basically the number of neutrons and the number of protons in AMU per atom. We have also the atomic mass unit, the AMU. It's basically 1/12, the mass of the most naturally abundant carbon isotope, which is 12. So for carbon 12, the atomic mass unit is 1, actually 1/12. Atomic weight, this is the third thing. It's basically the average, the weighted average of atomic masses of naturally occurring isotopes in AMU per atom or in gram per mole. And regarding these, basically 1 AMU per atom is the same as 1 gram per mole. So let's put all these information into one example, one simple one. So let's look at the boron. Boron is an element. First of all, what is this 5 here, guys? Can anyone tell?
Atomic number.
Atomic number, exactly. So it's the atomic number, okay? Atomic number, or Z, which is the same number as the number of protons and the same number as the electron in a neutral boron, okay? So it does not participate in any kind of reaction or something. Okay, what about this one? 10.811. What do you think, guys?
Atomic weight.
Atomic weight.
Exactly. It's not the atomic mass, it is the atomic weight, okay? Now let's tell the difference. Now, if you look around the world for element boron, you will see that the boron basically occur in two isotopes. One is called B10 and the other one is called B11. Okay. B10 means that we have 5 protons and 5 neutrons. This is the atomic mass. And the B11 meaning that we have 5 protons and 6 neutrons. Again, this is the atomic mass. But if you can just count all the boron around the world, you will find out that the B11 is basically account for 80% of them. So 80% of all boron is B11. And the remaining 20% of all boron around the world is basically B10. So the way to calculate the atomic weight in this case is just basically to do a simple calculation. And the calculation is as follows. So it's basically 20 over 100 times 10 plus 80 over 100 times 11. And if you calculate it, it will be something like 10.8, which is a very close approximation, okay? So this is for the boron, okay? This is for the boron. Let's look at, but the same principle applies to any other atomic weight for any kind of material or element. Let's say an example of cerium. Cerium has this natural abundancy, 0.185% for 136 cerium. This is the atomic weight, and this abundancy and this atomic weight, this abundancy and this atomic weight, and this abundancy and this atomic weight. He's asking to find out the atomic weight or the average atomic weight. It's basically we can do exactly the same thing, okay? So we say that 0.185 divided by 100 times 135.907 plus 0.251 divided by 100 times 137.906 plus 88.450 divided by 100 times 139.905 plus finally 11.114 divided by 100, 141.909. And that would be equal to 140.115 AMU per atom, which is same thing as gram per mole. Any questions, Shabab? Good. So this is basically how to calculate the atomic weight. اتفضل. Guys, in the future, if you have a question, just raise your hand so I can see it directly. I mean, sometimes you won't. Yeah, go ahead, Michal.
Okay, the first one. Why you didn't multiply it by 136?
Okay, so remember what we said before, okay? So the atomic mass is approximately the number of protons and neutrons, okay? But it's not exactly this one. So in this example, he's giving you exactly the atomic mass, okay? But in this one, as we said, it's approximately the same number of protons and neutrons. The same thing here. So it's 10.8, okay? But it's not exactly, it's a very good approximation. You can see, for example, it's 135.907. It's almost 136, okay? But as I said, it's not exactly, it's approximately a very good approximation.
Okay, thank
Okay,
you, Doctor.
Michelle?
Yes.
And if you find out, if you just plug in the numbers, you will find it's very approximate, I mean, the atomic weight. Any more questions, Shah? Good. Right. Let's look at the atomic model, okay? And we are going to focus on just the atom, okay? So one of the first and very useful and simplified model is called the Bohr model, Bohr atomic model. It's very well known. It's very easy to read, very easy to explain on, okay? And there are two main things about this model. Electrons are revolving around the nucleus. And regarding the position of the electron itself, the position is more or less well defined in the orbital. So we know the position of the electron. You might be asking what is the usefulness of this information. Once we introduce the other models, you're going to see the difference, okay? And this is one of the distinction. So one distinction is basically, one thing about the Bohr model is that the position of the electron is more or less well defined in the orbital. So at any time, you can tell me that this electron is exactly on this orbit. So we know it, the probability is 100%. And the other thing is that the energy of the electron is quantized, okay? The energy of the electron is quantized. You might be asking, okay, position we know, what does it mean quantized? The quantization of the energy is basically saying that the electron is permitted to have a specific value of energy. Let's look at this example here. So for example, here we have the Bohr model, okay? And this is the orbit. We can say that this is 1, and this is 2, and this is 3, okay? This is the shell, number of shells. So this is 1, 2, and 3. We say that the lowest energy in this case is when n equal to 1, which is this one here, which is minus 13.6 electron volt, okay? Minus 13.6 electron volt. Now, a number 2, or the shell number 2, it has an energy minus 3.14. When we say that electrons have to have a permitted or are permitted to have a specific value of energy, meaning that electrons can be here, can be here, can be here, but it cannot be here, okay? There's no way it can be here. Meaning, that's why we say that it has to have a specific value of energy. And this one can be derived from just simple mechanics, okay? Because there is an interaction between the electrons and the nucleus. And we can basically quantify this one, but it is beyond the course of beyond the course, the scope of this course. So again, the quantization meaning that the electrons are permitted to have a specific value of energy, okay? Not only this, so if the energy of the electron decided to go up into higher energy or to go down into lower energy, what does it say here is that it has to have, it's either to absorb energy or release energy. If it wants to go or to higher energy from this level to this level, not to here, there's no way it can stay here, okay, because there is no allowed energy state. So if it goes from here to here, it has to absorb energy, okay? It has to absorb energy. If it wants to go from higher energy to lower energy, then in this case, we say that it releases energy. It releases energy. Go ahead, Salama.
معلش يا دكتور الصوت في له مشكلة عندك واختلف فجأة صار لوب
اوكي طيب. هل الصوت مو واضح يا سلامة؟
ايوه يا دكتور.
ايه ما في صار في تشويش وصار في صدى في نفس الوقت.
اوكي اصبر شوي بس لاني انا مشغل هنا. طيب خلينا نسوي زي كذا. هل الصوت واضح الان مو واضح؟
نفس المشكلة يا دكتور.
لا
ستيل
يجي التشويش يا دكتور.
تشويش إيه.
في
وصوت.
تشويش.
وفي ديلاي لما تكتب.
افصل المايك وركبه.
ماني مركب المايك أنا بتكلم عن طريق اللابتوب. هل
إيه كذا
ممكن
ممتاز.
إنه النت ممتاز كده؟
إيه كذا
زين.
ممتاز.
ها ممكن لاني كنت مشغل التيمز برضو من الجوال في نفس الوقت ممكن. اوكي you're recording what's your sharing اوكي طيب هل الصوت واضح الآن يا شباب؟
إيه واضح دكتور.
طيب ممتاز. طيب اوكي طيب ما دام انه زي كذا يا شباب اللي عنده سؤال ممكن يتكلم مباشرة because I cannot see your hands okay. طيب so the atomic model we said that the Bohr model that has to have a specific value of energy, and if it goes up or down then basically it has to either absorb or release an energy. Now you see that this is minus 13.6, this is minus 3.4, minus 1.5, but you see the energy is coming again from the interaction between the electrons and the nucleus, and from electrons to nucleus, and from electron to nucleus, okay? Now my question to you is, what is the zero means here? What do you think, guys?
I think the center.
Is it the center? Okay, that's one answer, okay. What do you think, guys? So this is 1, and this is 2, and this is 3. One has the lowest energy. Go ahead.
I think it's the farthest, the furthest. It's the furthest orbit, and
The
cannot.
furthest orbit. Okay, so it's like here.
No, it's like.
Go ahead. You're on the right track.
It has no like attraction. No attraction power.
Exactly. So it means yes. So basically, the zero energy meaning here that it is unbounded, okay, to the nucleus, or it's free electrons, okay. So it can go basically anywhere. So that's why the zero. The zero means that it's unbounded, free electron. And again, guys, let me remind you: if you have a question, just shout it out, okay? I cannot see your hands. Okay. So this is the Bohr model, okay? It's very simplified, very useful to understand some physics, but it has some limitations. And one of the limitations is basically the nature of electrons itself. So here we are treating the electrons as particles, okay, as you can see here. But the question, is it particle, okay? Do you know Einstein, he got the Nobel Prize, isn't it? Do you know what was the Nobel Prize about for the Einstein? Does anyone know?
Relativity.
No. Relativity is something, but it's not about the Nobel. The Nobel Prize he got is something called photoelectric effect, okay? Yeah, it's somehow it's photoelectric effect. So basically, what was saying that the electrons, and after that, the Louis de Broglie, he further refined the model, okay, of the Bohr model based on this It was explored before that from experimental point of view, the electrons does not behave only as a particle, okay? The electrons behave as both particle and wave. تفضل.
دكتور we cannot hear you.
صوت رجع نفس الشيء.
ظاهر المشكلة.
It's retained as it's used. بعد رجع صوتك مشوش يا دكتور.
أتوقع والله العالم إنه النت حق الجامعة فيه مشكلة. طيب خلينا نسوي let's try to do something to...
الآن كويس يا دكتور.
هو الصوت يزين ويصير أسوأ كل شوية.
يروح ويرجع التشويش يعني.
طيب اجل بشتري ان شاء الله الميكروفون عندكم ان شاء الله تعالى، بس انه نحسن من الوضع هذا، مع انه اول مره تواجهني المشكله هذه، بس وات ايفر. اوكي.
لا دكتور، ما اعتقد المشكله الميكروفون، النت يمكن اكيد.
لانه ايه النت ممكن لانه مع اننا في المكتب حق الجامعه يعني، بالتالي
انا الحين قاعد اسمعك صح واضح يعني، بس لما تكبر اللي هو العرض وتكتب
ايوه
يصير
عن
ضعيف.
اجل النت المشكله. طيب الله يعين. انا ما ادري كيف ممكن نحل الموضوع هذا، لانه له علاقه بالنت، وانا فما تقول انه في البيت مثلا ولا زي كذا. طيب خليني نشوف.
لأنه يعني ما يأثر مرة، يعني نقدر نفهم الكلام صح، إنه في شوية تشويش خفيف، بس الكلام بالمجمل مفهوم
ان شاء الله تعالى. طيب ان شاء الله تعالى في انه التسجيل ما يكون فيه تشويش زي كذا. طيب let's try our best. okay. طيب so basically the electrons behave as both particle and wave. So that de Broglie, actually you can see a live interview with him if you are interested. Okay. But he's basically saying, okay, we know that the electron behave as both particle and wave. And in the Bohr model, he's treating the electron as particle only. The second thing, in the Bohr model, he said that more or less the position of the electron is known, but in the wave mechanical model, this is the name terminology of this model, the wave mechanical model, the position only described by the probability distribution or electron cloud. How can we see this? Let's look at this diagram. Okay, let's look at this diagram of the hydrogen atom. So we have the electrons here, we have the Bohr model, and here we have the wave mechanical model. In the Bohr model, as you can see here, this is the position of the electrons. And this is the probability. The probability is 1, is 100%. So we know the position of the electron. This is from the Bohr model, okay, the known position. But in the wave mechanical model, no, we don't say that we know the position for certain, but we know the probability of finding the electron in that position. You can see from here, the orbit, okay, it has the highest probability, not 1, not 100%, but it has the highest probability. But the electron can be here, can be here, can be here, can be here, but not at the nucleus. You can see it's 0, but it's somewhere here. And that's why you can see electron cloud, okay, electron cloud around the nucleus because of that probability, okay, because of that probability. So these are the main distinctions. Were you able to hear my explanation or not, guys?
ايه نسمع بس يشوش، وهذا المشكلة.
الله يعين. طيب. Okay. I will try to find out from the ICDC after the inshallah class. طيب. So from the wave mechanical model, state that every electron in the atom is characterized by 4 parameters, okay, quantum numbers. So the first one is called the principal quantum number, shell, or sometimes called shell, where n is equal to, okay, so n is equal to 1, 2, 3, or sometimes it's called KLM, especially if you're working with the X-rays, they more preferably use it as KLM, okay? So this is the only quantum number that is similar to Bohr's model, which describes the orbital size, okay? So you can see from here, from this diagram, so this is from Bohr model, okay? But it is applicable here because it's the same, okay? For the principal quantum number. So this is 1, 2, 3, and this is KLM. It's the same thing, okay? Sometimes we call it 1, 2, 3, sometimes it's called KLM. So the higher the number, the bigger the size of the atom, okay? So you can see 1 is small, but if you have 1 and 2, it's bigger now. 1, 2, 3 is bigger, and so on and so forth. So this principal quantum number describes the orbital size or the distance from the nucleus. The second one, we have the second quantum number. It is represented by L. So this is N, this is L, or sometimes called subshell. So it's basically N minus 1. So if the N is equal to 1, then the L is equal to 0. So maybe you might be more familiar with the terminology of 0, 1, 2, 3, but more familiar with the SPDF, okay? So this is basically describe the orbital shape. Let's look, for example, the S. In the case of the S, the shape is spherical, okay? The shape is spherical around the nucleus. But if you look at the P, for example, the shape is now nodal shape. And this cloud, this is electron cloud, again, guys, it's the probability of finding the electrons around this cloud, okay? So the electron might be in this cloud. Huh? Okay. Now it's difficult to know whether that's a question or just basically a slip of the tongue. Regardless, okay. Now this is the second quantum number. So it's 0, 1, 2, 3, 4, SPD, and describe the orbital shape. The S has spherical, the P has a nodal, the D has even more complicated shape, F is even more complicated shape. So this is the second quantum number. And the third quantum number is called magnetic. What do we say by magnetic? It's basically describe the number of possible orbital. So if you look at, for example, L equal to 0, so there's only one possibility. So this is for S, one possibility. But if you look at the P orbital, it has -1, 0, 1, and this one has 3 possibility. If you look at the D, for example, L is equal to 2, so -2, -1, 0, 1, and 2. It has 5 possibility. What do by 5 possibility, 3 or 1? So if you look at the S subshell, it has only one shape, okay? One shape. This is spherical shape. There is no other possibility. But if you look at the P, for example, we said that there are 3 possibilities. And for the P itself, it's basically, it can be along the x-axis, it can be along the y-axis, it could be along the z-axis. So there are 3 possibilities. The D is even more complicated, but we will not explain it here. So this is the third magnetic number, or the third quantum number. Finally, or the fourth quantum number, or sometimes called spin moment, is basically the electrons have to spin up and spin down, so plus half and minus half within within the subshell itself. Okay. Any question show up? Okay. So this is another way to look at it, okay? So it's similar to what we have explained, and you can, of course, look at it after the lecture. But this is just the main thing that I want to explain, that every electron has characterized by 4 parameters, okay? So the question is how to fill the electrons, okay? So from here, we can see the electron energy. We see that the 1 or the 2 has higher energy than 1, the 3 has higher energy than 2, 4 has higher energy than 3, etc., etc. But within each, there's subshells, and the subshells also, the the P has higher energy than S, the P has higher energy than S, P has higher S, and the 3 is higher energy than 2, 2 has higher energy than 1, okay? So how to fill the orbitals? So we apply the Pauli exclusion principle, which postulates that there is no energy state can hold more than 2 electrons with opposite sign. So on each state can hold 2 electrons, but they have to be in opposite signs, or the spin moment has to be different, okay? I will take an example about it just to explain it here. But when all electrons occupy the lowest possible energy state, we say it's ground state, and the SPDF can accommodate 2, 6, 10, and 14 electrons respectively. Okay, let's take an example of iron. Iron has 26 electrons. Okay, iron has 26 electrons. So if you want to fill the subshells here, if you want to fill the subshells, we start from the lowest shell, or from the lowest shell and the lowest subshell. So we put two electrons with different signs, different spin moments, and then we continue to add the rest of them, and we are left with now we are left with 6 electrons, and the way to fill it is like this. So this is one way to illustrate the distribution, or other way is maybe you are more familiar with, is just to write it this way. So 1s2, 2s2, 2p6, 3s2, 3p6, 3d6, and 4s2. Okay. So this is how to write the electron configuration of an atom. Most important among all these electrons are the electrons in the outer shell. It's called the valence electrons. All the reactions can happen within these valence electrons. It dictates the property, the electronic properties, other properties, chemical properties, all from these valence electrons. So for material scientists and for chemists or chemical engineers, you are more interested in these valence electrons because they happen to have they participate in the reaction and dictate the property. Here are some other examples of electron configuration of different atoms. And you notice something here that, for example, for helium, we say that it is stable, neon is stable, argon is stable, and krypton here is stable. When we say stable, because all the shells and subshells are filled with electrons. There is no basically possibility of adding electrons or taking electrons. They are satisfied with their electrons and shells. That's why it is stable, and that's why we call them inert gases, and that's why we call them inert gases, and they do not participate in any kind of reaction. Okay, but as you notice here, that most elements, the electron configuration are not stable. Okay, the rest of them are not stable. And the reason behind that is the valence or the outer shell is not filled completely. So you can see, for example, the lithium here. Lithium has 1s2 and 2s1. Okay, they are not filled completely. So in order to fill the outer shell completely, we can basically get rid of 1 electron. So we will end up with 1s2. We call them lithium plus because we took 1 electrons, or we can just basically add more electrons to become 1s2, 2s2, 2p6, and we say lithium -7. Okay, so this is how to fill the electrons. But in your opinion, guys, which one is easier, just to get rid of 1 electron or just to get 7 electrons?
Remove.
Remove. Yeah, lose 1 electron. Okay, it's much easier. Okay, but this is just to explain to you that why is it unstable, because it wants to reach to a stable. It wants to reach to the stable configuration, and there are 2 ways. But usually, of course, as you said, this is much easier just to lose 1 electron. In order to classify all the elements within specific groups, I would say we have the periodic table. So in the periodic table, the columns is basically has similar values. Okay, like for example here, we have lithium, sodium, potassium, rubidium, cesium, etc. So this one gives up 1 electron. Now, if you go to here, it gives up 2 electrons. If you go to here, it gives up 3 electrons to reach to the stable configuration. If you go to the other side, here accept 2 electrons, and this one here accept 1 electrons to reach to the stable configuration. So another way to see it, we say that if you go to the right, we call it electronegative element, meaning it's readily acquiring electrons to become negative ions. Okay, this is electronegative elements. Electropositive element on the other side, we say that it's readily give up electrons to become positive ions. Okay. Another way to see it again is just to develop something called negativity. Okay, the electronegativity of atoms. The higher the electronegativity, the larger the atom will acquire an electron. If you go from left to right, the electronegativity increases, meaning that as you go from left to right, the material wants to acquire electrons. Okay? If you go from basically bottom to up, the electronegativity also increases, meaning that it wants to acquire electrons. So this is the periodic table, and this is basically the electronegativity. Okay, the increase from left to right, electronegativity increases, meaning that it wants to acquire an electron. Electronegativity decreases, meaning it wants to get rid of an electron. There is a highly chance it wants to get rid of an electron. طيب, any question يا شباب؟
دكتور بس come again please. There is a high chance of getting rid and accepting.
Yeah, so basically, if you're going from left to, if the electronegativity increases, there is a higher chance that that atom will acquire an electron, okay? So it's like here, we said that it's electronegative element, okay? So it wants to acquire an electron. So if there is electronegativity is increasing, meaning that that atom wants to acquire electron more. For example, let me give an example. Here is the lithium, okay? The electronegativity, or maybe here is easier to see. Lithium, electronegativity is 1. Fluorine here, electronegativity is 4.1. So what do you think, which one wants to acquire an electron here? Want to get an electron?
Fluorine.
Fluorine, okay. Because it has a high electronegativity. It's the highest electronegative element, okay? So it wants to get an electron. So the higher the electronegativity, the more likely the atom will acquire an electron, okay? Is that clear? Sorry, I cannot see your name or anything because... okay, is that clear? طيب, so let's talk about just a different specification of this periodic table. We have the inert gas or the noble gas, which is here. It's reactive because they have stable electron configuration, as we have mentioned before. We have the halogens. Halogens needs 1 electron to reach to stable configuration. We have here basically the alkali metal gives up 1 electron. They're very reactive, gives up 1 electron to reach to stable configuration. ما حد قد شاف تفاعل الصوديوم مع المويه مثلا ولا الصوديوم ولا البوتاسيوم؟ ما حد قد شاف هذا الشيء. So basically it's very highly reactive, okay. بالضبط. هذا في الووتر، بس حتى مثلا لو حطيت حتى لو كان مو بس في المويه، لو حطيته في الهواء يحترق، اوكي. لو حطيته في الهواء ممكن يصير زي catch fire, okay, because it's very highly reactive to react with the air. So basically what it means is basically it's very reactive because it gives up 1 electron to reach a stable configuration. طيب, here we have transition metals, very interesting groups of metals. They have partially filled the electron state. Most of them conduct electricity and heat. And finally, we have these columns. They have characteristics between metals and non-metals depending on their valence electrons. So far we have talked about just a single atom for individual atom. But the question is, what if we have 2 atoms and we bring them together? What will happen, okay? And this is the second part of this chapter. So when we know about a single atom, now we have 2 atoms. What will happen? Let's take an example of sodium and chlorine. Both of them are unstable, okay? And if we look at the electronegativity, sodium has 1 and the chlorine has 2.9. So in that case, the sodium from far away, it wants to get rid of an electron, okay, to become positively charged ion. The chlorine, it wants to acquire an electron to become negatively charged ion. And whenever they are reacting with each other, they will form sodium chloride, which is basically where, يا شباب? Sodium chloride, where do you see it? ملح الطعام بالضبط اللي هو dinner salt. طيب. So basically this is the sodium and this is the chlorine. So from far away, sodium wants to give electron and the chlorine wants to acquire an electron. So the resultant is attraction, okay? There will be some attraction forces between them. So there will be attraction forces, they will try to pull each other, okay? To try to pull each other. Makes sense يا شباب? Okay. Okay. But once they become close to each other, يا شباب, there is something also plays a role here. So once they are come very close, what will happen is that even the sodium wants to get rid of an electron. There is some electron cloud here. And here also there's some electron cloud. So what will happen is that we have electron cloud, we have electron cloud. So these electron clouds will collide with each other. They want to basically repel. We push each other away because all of these electron clouds are negatively charged in general. So they want to push each other, okay? Electrons are negatives, so negatively charged. So they push each other away. They repel each other. So we have here some attraction forces and we have here some repulsion forces, okay? And then they will settle down, okay? They will settle to having, let's say, Fn, which is the net force. We have attraction force, we have repulsion force, and we explained just a moment ago. They will settle out whenever the net force is equal to 0, meaning that the attraction force, is equal to the repulsion force, okay? Whenever the attraction forces is equal to the repulsion forces, the net force is equal to 0, and we say now they are satisfied, and they reach to something called R naught, which is basically the distance between the center of the atoms. And this R naught is called the equilibrium distance, a very important one. Whenever you see some molecule radius or something, so this is the radius that we are talking about, okay? So this is the equilibrium spacing or equilibrium distance, 0.3 nanometer generally, okay?
So,
Go ahead.
yeah, what causes the equilibrium to happen between the repulsion and the attraction?
Because there is always a repulsion forces, there is always and attraction force. Attraction because both of them are liking each other, but the repulsion because electron cloud do not like each other. So whenever there is a net force is equal to 0, now there is an equilibrium of forces, okay? So they will stay at specific distance. And then it will basically satisfy. One will take an electron, one will get an electron, and they will satisfy at that specific position, okay? The exact physical reason why this is happening can be explained from the energy point of view, which we'll explain inshallah next lecture, start from next lecture. But let's say from the forces point of view, the net force is equal to 0. Usually, for example, the attraction force is positive, the repulsion force is negative. Whenever they are equal to each other, it becomes 0, and it will reach to R naught, which is the equilibrium spacing. Is that clear or not?
Yeah, clear.
Okay. طيب, one way to look at it is if we draw a diagram like this, okay? Bear with me here. Don't be scared from this diagram. So here in the x-axis, we have the interatomic separation, okay? Whether it's from here until we reach to this value here. So this is the interatomic separation. So as we said previously, if they are far away, they will attract each other. So there'll be some kind of attraction. The attraction force is this is the force in the y-axis. The attraction force is positive. So there'll be some attraction force here. On the other hand, when they come close to each other, the electron cloud basically repel each other. And that's why the repulsion force will start whenever they are very close to each other. This is the repulsion force. Now they're repelling each other. The more you bring them together, the higher the repulsion force, okay? But what we are interested in is the net force here. And you can see from the net force here, the summation of both forces, at first it will follow the attraction force because there is no significance of the repulsion force until to reach the point where the repulsion force kicks in, and then basically the summation will be something like this. And as we said, whenever the force is equal to 0, which is this value here, now this is called the equilibrium distance or the equilibrium spacing. This is the equilibrium distance or equilibrium spacing. And the R naught, which is this value here, is basically this value. Now, it's your turn, guys. Do you have any question?
Doctor.
Sure.
Where is the net force in this diagram?
Okay, good. So the blue one is the repulsion, is the attraction force, and the red one here is the net force. The red one is the net force. But as I said, before the repulsion kicks in, the net force and the attraction force is the same basically. صح ولا لا? But once the repulsion force kicks in, it's basically the summation of the two. So the red one is the net force, okay? This is Fn. And the blue one here is the attraction, and the green one here is the repulsion. Does that make sense or not?
And when they stabilize?
Stabilize whenever the net force is equal to 0, meaning it's here. So this is the force in the y-axis. Whenever the force is equal to 0, meaning it's stabilized now. This is the equilibrium distance. Everyone is happy. No more pulling or pushing each other.
Yes, now clear.
Okay, so starting from next lecture, I will go through this again, okay? And we'll go to talk about the energy. So convert the forces into energy. Let me do one thing.